Okay, so this question is going to get us to play around with functions a little bit. It's starting out quite nicely, just asks us to find the rule for h where h is equal to f of g of x. So, well, fx is just equal to log e of x, and gx is equal to x squared plus 1. So f of g of x is just literally substituting g of x into where the x is in f of x. Well, not h of x, g of x, and then we just get f, which is log e, and then we're just going to put this into this space here. So we just get this. It's quite an easy 1 mark. So our next part though, 2 marks, but even so, almost just as easy. Domain is essentially what is our restriction on x? What can x be? Well, in this situation, x can be whatever it wants. So we're just going to get a domain of R. It's pretty easy 1 mark as far as it goes. The range, now you might be tempted because you're thinking, well, this must be greater than 1, this must go up higher. But remember, this is a log function. So actually our range here, log of 1 is 0. So the lowest that this could ever be would be log of 1, or log to the base e of 1, which is 0. So the lowest this can ever reach is 0. The highest it can ever reach is still massive, still infinite. So there we go, that's another 2 marks in the bag, not too bad. Alright, next one. This is a show that, so I mean it's already given me the answer, so in ways this is another easy mark. Now, there's a couple of different ways to do this. The best way I'd say, start with the left hand side. Our h of x, if we remember, is log e x squared plus 1, and then we're going to add that to h of negative x, which is just basically going to be the same. Got to be careful with my brackets here. This is negative x squared plus 1. This is just going to be log e x squared plus 1, and this is going to be exactly the same. So actually what we've got is 2 lots of log e x squared plus 1. Now my right hand side would actually be log e x squared plus 1 all squared, which if we know our rules of logs is just 2 log e x squared plus 1. And then we can just say left hand side equals right hand side. So I've just proven that because this is equal to this, we've shown what they've asked for. So find the coordinates of the stationary point of h and state its nature. So to find the stationary point of h, we should be differentiating h and making it equal to 0. Well, h of x is equal to log e of x squared plus 1. Stating its natures is a little bit more messy though, so let's first figure this out. H dash of x is going to actually be 2x over x squared plus 1. Now when this is 0, this is a bit of a weird case, because to a certain extent this is only going to equal 0, like this side is only going to equal 0 when the top is equal to 0. And the top is only going to be equal to 0 when x is equal to 0. I mean, you could do some technically incorrect maths at this point and times this up to here, which would actually delete it altogether. And then you get this, which would tell you that x is equal to 0. But the other way is technically more mathematically incorrect, to not kind of do that disappearing act. Regardless, it's at x equals 0. So the stationary point would be at 0. And if we substitute this into here, we actually see that this would be 0, 0. Now, it's asked us to state its nature though. Now, if we think back up here, we know that our range is only from 0 to infinity. So we could see there that this would be a minimum point. But there are a few other ways we could do this. We could do this by a sketch, or we could do it by the way that I like to do it, which is we double differentiate, which would give us, technically this is going to be u dash v, take v dash u all over v squared. So I'm going to need to use some extra space over here. U being 2x, v being x squared plus 1, v dash being 2x, u dash being 2. And so we're going to get u dash v, so 2 times x squared plus 1, take v dash, which is 2x times u, which is 2x. So we get that all over v squared, so all over x squared plus 1 squared. Now if we substitute in our point to this, our x value, if h double dash of 0 is greater than 0, this implies it's a minimum. And if it is less than 0, it implies it's a maximum. So we can see that when we actually substitute in 0 here, we're going to get two lots of 0 plus 1, take away two lots of 0 squared, all over 1 squared. So we can see that this is greater than 0, therefore it's a minimum. So it's a local minimum. All right. So this has given me this unusual definition of k, and then asked me to find kx, k to the negative 1, where kx is this. So k to the negative 1 is asking me to inverse it. So the first thing I'm going to do is what I do when I inverse, which is switch the values around and write it back out. And now for me to inverse this, well, this is just going to be y squared plus 1 is equal to e to the power of x. So we take 1 off both sides, and then we square root. Now, the natural expectation here would be, I think most people would be thinking this, but the difference is we have got a restriction up here. We're told that k is always negative. The most that kx is allowed to equal is 0. So in truth, this whole thing of positive and negative in front of this isn't necessarily needed in this case. We can actually reject any positive answers. So our k of negative 1 of x is actually just equal to all of the negative things. So this is just going to make sure that this thing is negative every time, which fits in with our rule of k. So there's our answer. Now, the domain and range of this, well, really we've been given the range of it here. So that made it quite easy for one of those marks. However, our next bit is a little bit more messy, because we've got to think, well, actually, this is an inverse of our function, which we started with. Now we know that the domain and the range flip when you inverse it. So if you think about it, going back up to the start of our question now, we were told that our range was r. So the inverse, this will come the domain. So the domain of our inverse will actually be 0 to infinity. So what we get for our final answer here is our domain is 0 to infinity. So this feels kind of weird that the domain and range would be the other sort of ends of the scale, but that's our answer.